GP2, then I would get nu equals to 3 integer quantum Hall in 2 dimensions. The reason is following. The reason is following is that so as I mentioned before, the boundary for this theory is a 5 + 1 dimensional self-dual boson. Okay, self-dual boson. So we have to solve this self-dual condition to find all the propagating mode as a 5 + 1 dimensional boundary. So now, if I reduce my theory, compactify the 4 dimensions, then this self-dual equation will become some linked equation between the 1 + 1 dimension and the 4-dimensional internal space. If I get a self-dual solution in the 4-dimensional internal space, I would get a chiral mode on the 1 + 1 dimensional space. But if I get an anti-self-dual solution on the 4-dimensional manifold, I would get an anti-chiral mode on the 1 + 1 dimensional mode. So it means that whether the final theory in the 1 + 1 dimensional boundary is chiral or not will depend on the difference between the self-dual solution and anti-self-dual solution on the 4-dimensional manifold. Okay, so now you can see this is like the index theory now. Okay, some solution minus some other solution. This difference matter, and this difference will depend on topology of the manifold. Okay, some index theory. So there's some index theorem guarantee that on some manifold with certain topology, I'm guaranteed to get some chiral mode in the reduced 1 + 1 dimension. Otherwise, we will not. So, for example, you can also try this. You can take a 4 + 1 dimensional integer quantum Hall state and compactify 2 dimensions and check whether you get the chiral mode on this 1 + 1 dimensional space or not. Turns out it's not always true. Okay, you have to design a special topology for the 2-dimensional compactify on, or insert some flux in that 2-dimensional. So it's not a trivial game to play. Okay, it all depends on how you compactify a system on 2 dimensions. Okay, there's also some index theorem. Okay. Okay, so now we know that in every 4K + 2 dimensional space, we have a boson state beyond the group cohomology. Okay, and I label the state as a BE 4K + 2. Okay, so knowing this state, we can use this state as base states, and we can use this state to construct other SPT states in other dimensions. Okay, and they are all beyond group cohomology because they are based on these states without any symmetry, and they are beyond group cohomology. So the most well-known state like that is already mentioned several times in this conference is the Central and Vishwanath's SPT state in 3 dimensions with time inversal symmetry. So most naively, this state can be viewed as a time inversal symmetry, time inversal invariant system. I first break time inversal, then I consider the 2-dimensional time inversal symmetry breaking domain wall, then I decorate the domain wall with this EA state, with the EA state, and then I proliferate the domain wall. Then I would get this SPT state in 3 dimensions, and this time inversal symmetry. But now this state will have time inversal symmetry. It's no longer an invertible topological order anymore, okay, because this time inversal symmetry is protected. Okay. But because this state has been mentioned several times in the conference, so I will not get into much details about it. But we can just go further. We can come up with a systematic way to construct all these states. For example, in every 4K + 4 dimension, we can easily construct a bosonic SPT state with U1 symmetry. We can view this state as proliferating the U1 vortex. For example, we can start with a superfluid phase, and I just proliferate the U1 vortex. However, I decorate the U1 vortex with this state in it. Okay, with this state in it. Okay. So what kind of field theory describes this physics? Okay. It's precisely this term. This topological term will describe this physics. So yesterday I showed you that a nonlinear sigma model field theory I developed actually is very good at describing topological defect decorated with something. Okay, remember that? Okay, yesterday I showed you that the ordinary sigma model, the physical meaning for the term simply means that the topological defect of some components is decorated with some term of some physical of some other components. So same thing happens here. This is a topological term I can write down for this state. And this state precisely means that the vortex of this N1, N2, so the N is a O2 vector. So vortex of N1, N2 will carry will carry this state. Okay, will carry this state. And let's, for example, let's take k equals 1. Okay, k equals 1 is the 8-dimensional state. Sorry. K equals 0. Okay, it's a 4-dimensional state. For 4-dimensional state, a vortex will be a 2-dimensional membrane. So it's the right dimension to be decorated with the EA state. Okay, so this theory describes the precise physics. Of course, this is only topological term. There are other terms which are ignored, but those terms will take care of the spectrum. Because those terms will guarantee the system will be a gap system, and this topological term will drive the gap system into some non-trivial SPD state. Okay, and also, so if I couple this O2 vector to a U1 dynamical U1 gauge field, if I couple the dynamical U1 gauge field, and also couple the system to gravitational field, then as the boundary, there will be some mixed gravitational and U1 anomaly. So mixed gravitational U1 anomaly.
So you say it's a mixed gravitational anomaly. You mix the transformation and then it's anomalous. By example, transformation.
Yeah, I think it means that gravitational anomaly means that energy moment tensor is not conserved, right? But the mixed means that energy moment tensor is not conserved only when there is a flux. Right, so the partial T equals to some F times R over R or something like that. Right, it's a mixture. So it's a mix between the U1 flux and the gravitational curvature. Okay, so let's keep going. Then in every 4K plus 6 dimension, there's also a bosonic state with the U1 symmetry. Okay, this state can also be viewed as starting from superfluid phase. Then I just try to proliferate the U1 vortex. But now, for example, if I take k equals 1 or k equals 0, if I take k equals 0, then the U1 vortex will be a 4-dimensional object. Okay, the 4-dimensional object. So 4-dimensional object does not seem to be able to be decorated with a 2-dimensional EA state. Okay, because the 4-dimension cannot host a 2-dimensional EA state. However, if we consider the intersection between two vortexes, okay, every vortex is a 4-dimension, then the intersection between two 4-dimensional objects in 6 dimensions will be a 2-dimensional object. So I can just decorate the intersection between two vortices with the 2D EA state, and this physics precisely described by this topological term. Okay, it's still a mixture between n dn with dn with dn and this term. Okay, this is a topological term. This describes decorating the intersection between the vortex line and this EA state. Okay. Okay, let's see one more example. In every 4K plus 5 dimension, let's take k equals 0. Let's take k to the 5 dimension. There is a bosonic state with time inversal symmetry. Okay, time inversal symmetry. And the field theory is this. Okay, this is field theory. And the vector n will change sign under time inversal. It will change sign under time inversal. So what this term means is that it means that in 5 dimensions, let's consider a hedgehog monopole of this vector n. In 5 dimensions, this hedgehog monopole is a 2-dimensional object. Okay, in 3 dimensions, a hedgehog monopole is 0 dimension. So in 5 dimensions, hedgehog monopole will be 2 dimension. Okay, this requires some spatial, you can close your eyes and imagine that. So we can just decorate that defect with the 2D EA state, this topological term we got. Okay, so we can see that this actually is a pretty systematic way of constructing all the bosonic SPD states beyond group cohomology. Okay, they all boil down to terms like this. However, there's one more base state which I didn't mention yet. So I said that in every 4K plus 2 dimension, there is a base state. And the base state is the EA state and 6D EA state and a state like that. Those states have Z classification, and those states do not need any symmetry at all. But it turns out that in every 4K plus 4 dimension, there's also a base state. Okay, but this base state has Z2 classification now. Okay, this, for example, in 4 dimension, we can write down this Chern-Simons theory. And B, in 4 dimensions, this B is a rank 2 tensor, it's a rank 2 gauge field. We can write down this field theory. And K is simply an antisymmetric matrix. It's simply an antisymmetric matrix. Okay. Okay. then this theory is also a non-trivial invertible topological state. Okay? And actually, this theory when k equals 0, this theory actually was carefully studied by this paper, and Brian Swingle is one of the authors. And they studied this state k equals 0, and the boundary of this state is a 3-dimensional photon state with all excitations are fermion, which means that the monopole and the charge and ion are all fermion. And this all fermion state was first discovered by Wang and Cenke. Okay, and they wrote down field theory for such a state. Okay. But this field theory can generalize to all 4k plus 4 dimensions. There's no problem with that. Okay. So this means that in every even dimension, we have the base states. The base states are bosonic short-term entangled state or bosonic invertible topological order without any symmetry. In every 4k plus 2 dimension, those states are Z classification, but with every 4k plus 4 dimension, those states are Z2 classification. Okay, they are described by this equation and also the equation I showed you before. Okay, so knowing these base states, we can just use nonlinear sigma model, the mixture between my nonlinear sigma model and those transition theory to construct all kinds of bosonic SPT beyond group cohomology. And the physical meaning of those states is just we decorating all the base states in all kinds of defects. Domain wall, membrane, vortex, monopole, everything you can imagine. Okay, and all these states as the boundary will have a mixture anomaly between gravitational anomaly and also some gauge anomaly. Okay. And this is a table we obtained using our strategy of construction of classifying the states. Here I only listed those states beyond group cohomology. Okay, there's another table which I showed you yesterday within cohomology. So those states are described by the nonlinear sigma model only. They do not involve any transition theory. Okay, but here, by mixing the nonlinear sigma model, all the vectors, and also the transitions, I would get a new table like this. Okay. This table is largely consistent with Xiaogang's table he showed last night in the last talk, with a few exceptions. So in these cases, the black ones are our results and the blue ones are Xiaogang's results. We have little difference. Okay, so there's something more that we need to study. Okay, but I'm willing to bet with Xiaogang.
So I think this my result may be a little more than 1 year because there's another bosonic ITO state is in 1 plus 4 dimension.
Yeah, that's the one here, right? That's the one here. That's this one. That's this one. That's this one. Yeah. So my table already has this one, and already has all the SPT, constructed using this one. 4 plus 1D. This is rank 2, 2, 3, 4, 5.
So this is I see. So this is a Z2 classification.
Yeah, Z2 classification. Yeah. So my table already has all the states constructed with both the one I showed you before and this one.
Okay, now
Yeah. Okay. So here's the table. So we have a classification and for all these states beyond cohomology. Okay. So any question for this part before I move on to the next subject?
In the process of constructing this table, did you use some specific model and try to say the result?
Just field theory, right? Just this kind of this kind of field theory.
Right.
Yeah, we just find this kind of field theory with the right dimension and try to assign the symmetry on this end to make sure the entire system is invariant under the symmetry transformation. Right. And we're going to find out how many transformations we can find.
Whether the result is the most general one, the conclusion you get.
Well, I mean, I'm doing the best I can. So it means that I classified all the states that can be constructed this way, but I cannot prove they are states which cannot be constructed this way. Yeah.
So maybe let me check out this. So the table you list, except the one line, seems consistent with the blue entry of my table. Except this you want send it directly to.
Sorry, say again. This this one.
Yeah, remove an outline. I think I have a bug. I make some stupid error in that text.
Okay.
I need to correct the results. But the other two, my table have an extra one. That extra probably corresponds to the red entry.
I didn't understand what the red entry is in your table actually.
Red entry means it's a beyond group actually, it's probably it's beyond the minimal declaration. And so all those states can be all the blue entry states can be obtained by the minimal declaration. But the one way to understand the minimal declaration is that if you do dimension reduction, you make a proper symmetry twist in some manifold, you get an invertible topological state of the other manifold. That's confusion probing from the group. So you do the symmetry twist using group in some proper manifold, but you think space-time as say M1 plus M2. You make symmetry twist on M1, do dimension reduction, you get a proper ITO on M2. So ITO is your response, your result. But then there is an issue that there are some states cannot be distinguished by this kind of probe. So there are possible two different SPD states which have same kind of response over this time. And so those are so-called red entry. And so there's
What confused me is that in your table actually some red entry have the same topological terms with the blue ones. 1/2 W1
well,
C1
different. Sometimes have different topological in the following. If using this nonlinear sigmoidal construction, they always correspond different nonlinear sigmoidal topological. This G cross SO. And the issue is that whether the distinct SPD phase can all be probed by this kind of dimension reduction probe. I consider space-time as an M1 plus M2, then making symmetries on M1, measure ITO on M2. Can you use in this way to distinguish all possible SPD states? And there's a possibility.
They are even more twisted, and you cannot.
The things that here you're using the twist, using symmetry twist on M1, and using parameter twist on M2, using this particular twist to probe SPD states. And this is not most general twist. So there are some SPD states with mixed gauge gravitational anomaly, but their combination, their probe has to be more complicated. It cannot be probed by this decoupled dimension reduction twist. So you cannot use space time as M1 plus M2. You have to use this some generic space time with some generic gauge twist and gravitational twist, and maybe there are some topological lines which don't have a simple separation. But I don't have too much understanding of this. It's just I wish the red entry is not there, but after some calculation is there, but my calculation could be wrong. So I tried to calculate the red entry away, but I couldn't at the moment.
Anyway, the real life is always more complicated than what we hope.
But the U1 semi-SD tool, I looked at that paper. I think that makes sense. I didn't miss the tool there.
Okay. Okay, so let me move on to the next subject, which is interacting fermion SPD. So far, I focused on the bosonic SPD. So let me move on to fermion SPD, and let me emphasize that interaction is really the key word here. I want to re-emphasize that it's interacting fermion SPD, and the connection to standard model and grand unified theory. So let me pretend I'm a high energy guy and try to introduce to you standard model, what standard model looks like. Okay. So in standard model, there are 3 generations of fermions, and actually we can do a particle hole transformation on the right-handed format and make all the right-handed format into a left-handed format. But this only can be done in 3+1, in 1+1 cannot. Okay, so effectively, in standard model, when we look at energy scale much higher than electron weak, then effectively every generation has precisely 16 massless left-handed chiral fermions if you assume the right-handed neutrino exists. Actually, in the grand unified theory, SO10 grand unified theory, these 16 fermions form precisely the spinor representation of the SO10. Okay, let me count for you. In the generation 1, we have an up-down quark. They have 3 colors, and also left hand and right hand. But as I said, we can do a party hole transformation, make the right hand into left hand. So, and also electron neutrino, and the left and right hand. We assume this guy exists. Then there's a 16. Okay, chiral form. So it means that standard model every generation, including the right-hand neutrino, will have 16 left-handed chiral form. And they couple to gauge field in a chiral way. Okay, the gauge coupling is chiral. Okay, gauge coupling is chiral. So this theory is well known that this theory is very hard to regularize on a 3-dimensional lattice. Because on a 3-dimensional lattice, usually, if we want to realize left-handed fermion, we also get the right-handed fermion coupled to the same gauge theory. It means that we would get a non-chiral gauge coupling. Okay. So in condensed matter system, in the last few years, there's one system is very famous called a wild semi-metal. It's pretty much a lattice construction for the wild fermion. Okay. So in this kind of system, in the same momentum space but a different momentum point, a different momentum, and one momentum we have a right-handed wild fermion, the other momentum have left-handed chiral fermion. Okay, they always come in pair. Wild semi-metal. Okay, so this is one condensed matter illustration of why it's hard to regularize only the left-handed fermion on the 3-dimensional lattice. Okay, but there's one quite popular alternative. Because the no-go theorem says that there has to be a mirror sector. We have to realize the mirror sector, but didn't tell us where the mirror sector has to be. So we can just spatially separate the mirror sector into 2 parts. For example, I can just realize the standard model or the grand unified theory on the 3-dimensional boundary of a 4-dimensional bulk. And the bulk could be some topological insulator, topological superconductor, whatever, but it has a boundary state. So it means that, but suppose I start with 4+1 dimensional integer quantum Hall, then there's no problem of realizing 3+1 dimensional chiral fermion on one of its boundary. However, there will be a right-handed chiral fermion on the bottom boundary. So we don't really get a chiral theory, but we just separate them a little bit. But this approach still is not satisfactory in the following sense, because actually, it requires a very, very subtle adjustment of the 4th dimension scale. If the 4th dimension is too large, okay, then the gauge boson in the bulk will be gapless. It will interfere. It will interfere with the boundary standard model and grand unified theory. So we don't want that. But if the 4th dimension scale is too small, then the 2 boundaries will talk to each other and annihilate each other. Okay. So again, we are in a difficult position. How do we adjust the 4th dimension? Okay. So the key question we can ask is that is it possible for us to gap out the mirror sector on the bottom boundary without affecting the top boundary at all? Okay. Is that possible at all? Okay. If not possible, then perfect. We just gap out the mirror sector. We only have the top surface. Okay. But turns out this again is not very easy to do. The reason is that the most standard way to gap out some Dirac fermion or wild fermion is by condensing some boson, and the boson will couple to some mass term of the fermion. Okay, and for the chiral fermion, the mass term is precisely pairing term. Okay, some kind of pairing term. Okay, so it means that in the mirror sector, we can just condense the boson phi, which couple to this. Okay, it will gap out the mirror sector completely. However, nothing forbids this phi to also couple to the top surface. Okay, the phi will also couple to the top surface and gap out the top surface immediately, no matter how small phi is. Okay, no matter how small phi is, as long as phi gap out the bottom surface, it also gap out the top surface. Okay. So in condensed matter, we call this the proximity effect. Okay, anyway, so now the question becomes this. So can we gap out the middle sector by interaction, by short-range local interaction? However, when the bottom surface is gapped out, the fermion bilinear quadratic fermion mass operator does not gain any expansion value. Is that possible? If this is possible, then it means that I can gap out the bottom surface without condensing any boson, which coupled to any fermion mass. Right? And it means that I don't have to gap out the top surface. I can only gap out I just have to gap out the bottom surface. Okay, there's no boson which to gap out the top surface. Okay. Okay, so this is dream. But actually, translate this goal into condensed matter language. It means that we must argue the following thing. We must prove that the bulk topological insulator or the bulk topological superconductor is non-trivial without interaction, but it becomes trivial under interaction. Okay? So first of all, let me say that the bulk topological order is non-trivial without interaction. It means that both the top and the bottom surface must be gapless. But it becomes trivial under interaction. It means that once I turn on interaction, short range full from interaction, the bulk becomes trivial. It means that I can gap out its boundary now. So all I need to do is to turn on this interaction, but make it stronger on the bottom surface and make it weaker on the top surface. Okay, we know that for a weak interaction for 3+1 direct fermion, it's going to be irrelevant. It will not gap out anything. But for strong enough, it may do something, because it can flow to a strongly coupled fixed point. So all we need to do is to make the interaction stronger here and weaker here. Okay. Let me also remind you that if I just condense the boson, it doesn't help to make the boson stronger condensate here, weaker condensate here, because the boson condensate is relevant perturbation. An infinitesimal phi condensate on the top surface will gap out top surface immediately. It's relevant. However, for interaction it's different. For from interaction, it has to be strong enough to gap out either boundary. Okay, so I can make it stronger here and weaker here. Okay. So this is a logic. So we just need to find a topological insulator, non-trivial without interaction, and trivial under interaction, and it has all the right symmetry to host the standard model or the gradient define theory. Okay, that's the goal. Okay, that's the goal. So Xiaogan has a similar logic presented in 2013, but he has a very different way of dealing with interacting TI from me. So let me just show you my way of how to understand this kind of interaction-reduced classification of a topological insulator. Question?
Yeah, real world fermions are massive.
Say again?
In the real world, fermions are massive.
I'm just looking at the energy scale way higher than any Higgs mass or
Yeah, but I mean, isn't it possible that just really small things you just get passed by some other?
if something is really small and fine-tuning, right? Well, I don't want to fine-tune.
I don't know if it's especially far away, it may not be that fine tuned.
Far away compared with what scale?
I'm not sure, but
Well, I mean, far away, as I said, far away, the photon will become very low energy in the bulk. Right? It again will interfere.
yeah, it's not clear, but you can't specify all these things.
Yeah.
The mass
Let-
term relate to the breaking of gates and what the kind of say that after fermion get a mass term, the gates
Anyway, I'm not saying that there's no room to tune this fourth dimension scale to make it work. But that's a really boring way to do that. Yeah, I'm showing you, I think, the more interesting way of doing this. You don't have to tune anything. You can make it small. That's
I mean, what Cenke talked about is before all the gates, if you do not break any gate symmetry, you know what happens. Yeah. And I don't know, actually, I don't know this some model very well, because in order for certain fermion to get a mass term, probably certain gate symmetry has to be reduced. So, like, say, for example, the SU2 weakened by the gate symmetry broken in order for it to get a mass term. If you do not break SU2 weakened gate theory, whether fermion can get mass term. So I think this is a situation where before you break any gate symmetry,
Yeah, before you get anything.